Section 210.24 of the National Electrical Code, specifically the 2020 edition, underwent a significant change concerning receptacle outlets. Prior to the 2020 update, the code contained a sentence that proved to be unenforceable, causing confusion and inconsistency in its application. The specific wording of the previous iteration of 210.24 included the statement, "Receptacle outlet shall not be installed in the floor unless approved." The core issue with this statement lay in the lack of a defined standard or criteria for what constituted an approved receptacle outlet in a floor installation. This ambiguity essentially rendered the rule unenforceable, as there was no objective measure or universally accepted guideline to determine compliance. Different interpretations arose among inspectors, contractors, and other stakeholders, leading to inconsistent enforcement across various jurisdictions. The absence of a clear definition created a situation where the approval of floor receptacle outlets became subjective and dependent on the individual judgment of the authority having jurisdiction, or OJ. In recognition of this problem, the 2020 National Electrical Code addressed the unenforceable language in 210.24 by removing the problematic sentence altogether. The intent behind this change was to eliminate the ambiguity and place the responsibility for determining the acceptability of floor receptacle outlets directly with the AHJ. This shift empowers the AHJ to evaluate floor receptacle installations based on local conditions, specific safety concerns, and any applicable standards or regulations within their jurisdiction. By removing the unenforceable code, the 2020 NEC aims to promote greater clarity and consistency in the application of electrical codes related to floor receptacle outlets. The AHJ now has the authority to establish specific requirements or guidelines for these installations, ensuring they meet the necessary safety standards and address any potential hazards. This approach allows for a more tailored and responsive regulatory framework that can adapt to the unique challenges and considerations of different environments. It's important to understand the implications of this change for electrical contractors, inspectors, and other professionals involved in electrical installations. They should be aware that the approval of floor receptacle outlets now rests solely with the AHJ and that they must comply with any specific requirements or guidelines established by the local authority. Furthermore, it's advisable to consult with the AHJ early in the planning stages of any project involving floor receptacle outlets to ensure compliance and avoid potential delays or complications. To summarize, the 2020 National Electrical Code addressed the issue of unenforceable code in Section 210.24 by removing the ambiguous statement regarding approved receptacle outlets in the floor. This change places the responsibility for determining the acceptability of floor receptacle outlets with the AHJ, promoting greater clarity, consistency, and adaptability in the application of electrical codes. First, it's important to define what an AHJ is. The OJ, or authority having jurisdiction, is an organization, office, or individual responsible for enforcing the requirements of a code or standard, or for approving equipment, materials, and installation, or a procedure. The AHJ is often a local building inspector, fire marshal, or electrical inspector. They are responsible for ensuring that electrical installations are safe and comply with the National Electrical Code, or NEC, as well as any local codes or regulations. Now that we have defined what the AHJ is, let's continue with the discussion of Section 210.24 of the NEC. This section covers the requirements for branch circuits supplying receptacles. A branch circuit is the circuit conductors between the final overcurrent protective device protecting the circuit and the outlet or outlet. Branch circuits are classified according to the maximum permitted ampere rating or setting of the overcurrent device. The common ratings for branch circuits are 15 amps, 20 amps, 30 amps, 40 amps, and 50 amps. The 2020 NEC, as we discussed earlier, removed the unenforceable code in 210.24, which stated that receptacle outlets shall not be installed in the floor unless approved. This code was unenforceable because there was no way to determine what constituted an approved receptacle outlet in the floor. The 2020 NEC change removes this unenforceable code and leaves it up to the AHJ to determine whether or not receptacle outlets in the floor are acceptable. This change gives the AHJ more authority to make decisions based on the specific circumstances of each installation. It also puts the responsibility on the installer to ensure that the receptacle outlets in the floor are installed in a safe and workmanlike manner. There are a number of factors that the AHJ may consider when determining whether or not to approve receptacle outlets in the floor. These factors may include the type of flooring, the location of the receptacle outlets, and the type of equipment that will be plugged into the receptacle outlets. The AHJ may also require that the receptacle outlets be installed in accordance with specific instructions from the manufacturer. It is important to note that the 2020 NEC change does not mean that receptacle outlets in the floor are now automatically approved. The AHJ still has the authority to deny approval if they believe that the installation is not safe. If you are planning to install receptacle outlets in the floor, it is important to contact the AHJ to determine what requirements they have. This will help to ensure that your installation is safe and compliant with the NEC. The removal of the unenforceable code in 210.24 is a positive change for the electrical industry. It gives the AHJ more authority to make decisions based on the specific circumstances of each installation. It also puts the responsibility on the installer to ensure that the receptacle outlets in the floor are installed in a safe and workmanlike manner. As an additional note on the types of receptacles that are found in the NEC, tamper-resistant receptacles are required in dwelling units. The requirement for tamper-resistant receptacles is in 406.12. These are designed to prevent children from inserting objects into the receptacle slots. This helps prevent electrical shock. Ground fault circuit interrupter, or GFCI, protection is required for receptacles in certain locations such as bathrooms, kitchens, and outdoor areas. The requirements for GFCI protection are in 210.8. GFCIs are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. Arc fault circuit interrupter, or FSI, protection is required for branch circuits that supply dwelling units. The requirements for FSI protection are in 210.12. FSIs are designed to protect people from electrical fires by detecting arc faults and interrupting the circuit. In summary, the changes to Section 210.24 in the 2020 NEC reflect an effort to improve the clarity and enforceability of electrical codes. By removing the vague language regarding approved floor receptacle outlets, the NEC empowers AHJ to make informed decisions based on local conditions and safety concerns. This ultimately promotes safer and more consistent electrical installations. It is important for electrical professionals to stay up to date with the latest NEC revisions and to consult with their local AHJ to ensure compliance with all applicable codes and regulations. Another important aspect to consider in electrical installations is proper grounding. Grounding provides a low impedance path for fault current to return to the source, which helps to protect people from electrical shock and equipment from damage. The NEC specifies the requirements for grounding in Article 250. It covers everything from grounding electrode systems to equipment grounding conductors. One of the most important components of a grounding system is the grounding electrode. This is a conductive object that is buried in the earth and connected to the electrical system. The grounding electrode provides a direct connection to the earth, which helps to dissipate fault current. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. Another important component of a grounding system is the equipment grounding conductor, or EG. This is a conductor that connects the non-current carrying metal parts of equipment to the grounding electrode. The EGC provides a low impedance path for fault current to return to the source, which helps to protect people from electrical shock and equipment from damage. The NEC specifies the size and type of EGC that is required for different types of equipment. Bonding is another important aspect of electrical safety. Bonding is the process of connecting together all of the non-current carrying metal parts of an electrical system. This includes things like metal conduits, metal enclosures, and metal equipment frames. Bonding helps to create a low impedance path for fault current to return to the source, which helps to protect people from electrical shock and equipment from damage. The NEC specifies the requirements for bonding in Article 250. It covers everything from bonding jumpers to bonding bushings. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when a circuit is carrying more current than it is designed to handle. Short circuits occur when there is an unintended connection between two conductors in a circuit. Overcurrent protection devices will trip or blow when the current in a circuit exceeds a certain level. This interrupts the flow of current and prevents damage to the circuit and equipment. The NEC specifies the requirements for overcurrent protection in Article 240. It covers everything from the selection of overcurrent protection devices to the installation of overcurrent protection devices. Understanding voltage drop is crucial for designing safe and efficient electrical systems. Voltage drop is the decrease in voltage that occurs along a conductor due to the conductor's resistance. Excessive voltage drop can cause equipment to malfunction, lights to dim, and motors to overheat. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Feeders are the conductors that carry power from the service entrance to the branch circuits. The amount of voltage drop in a circuit depends on several factors, including the length of the conductor, the size of the conductor, the current flowing through the conductor, and the conductor's material. Larger conductors and shorter distances result in less voltage drop. Copper conductors have lower resistance than aluminum conductors, resulting in less voltage drop for the same size conductor. Calculating voltage drop is essential for ensuring that equipment receives the proper voltage and operates safely. Several formulas and online calculators are available to help with voltage drop calculations. Proper wiring methods are essential for ensuring the safety and reliability of electrical installations. The NEC specifies the approved wiring methods for different applications. Some common wiring methods include non-metallic sheathed cable, also known as Romex, which is commonly used in residential wiring. It consists of insulated conductors enclosed in a non-metallic sheath. Metal-clad cable, also known as MC cable, is similar to Romex but has a metal sheath for added protection. It is often used in commercial and industrial applications. Conduit is a rigid or flexible metal or plastic tube used to protect conductors. Conduit is required in many commercial and industrial applications, as well as in some residential applications. The NEC specifies the types of conductors that are permitted for different applications. Conductors are typically made of copper or aluminum. Copper conductors have higher conductivity than aluminum conductors, but they are also more expensive. The NEC also specifies the ampacity of conductors, which is the maximum amount of current that a conductor can safely carry. The ampacity of a conductor depends on its size, material, and insulation type. Proper labeling and identification of electrical equipment is essential for safety. The NEC requires that all electrical equipment be labeled with its voltage, amperage, and other important information. This helps to prevent accidental contact with energized parts and to ensure that equipment is used safely. Circuit breakers and disconnect switches must also be clearly labeled to indicate the circuits they control. This helps to prevent accidental shutdowns and to ensure that the correct circuit is de-energized when performing maintenance or repairs. Working safely with electricity is paramount. Always de-energize circuits before working on them. Use properly insulated tools and equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. Never work on electrical equipment in wet or damp conditions. If you are not comfortable working with electricity, hire a qualified electrician. Electrical safety is not just a matter of following the NEC. It is also a matter of using common sense and taking precautions to protect yourself and others from harm. By following the NEC and using safe work practices, you can help to prevent electrical accidents and injuries. Finally, it is always a good idea to consult with a qualified electrician for any electrical work that you are not comfortable doing yourself. Electricians have the knowledge and experience to safely and properly install and maintain electrical systems. They can also help you to comply with the NEC and other applicable codes and regulations. In addition to the topics already discussed, let's delve into some other important aspects of electrical systems and the NEC. Electrical panels, also known as load centers, are the heart of an electrical distribution system. They receive power from the utility company and distribute it to various branch circuits throughout a building. Electrical panels contain circuit breakers or fuses that protect each circuit from overloads and short circuits. The NEC specifies the requirements for electrical panels in Article 408. This includes requirements for panel location, working clearances, and overcurrent protection. It is important to choose the right size electrical panel for your needs. The panel must have enough capacity to handle the total load of all the circuits it serves. It is also important to choose a panel that is listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or all. Surge protection devices, or SPDs, protect electrical equipment from voltage surges, also known as transient voltages or spikes. Voltage surges can be caused by lightning strikes, power grid switching, and other events. SPD divert surge current away from sensitive equipment, protecting it from damage. The NEC requires SPD in certain applications, such as in dwelling units and at service entrances. The requirements for SPD are in Article 230.8 and Article 285. There are different types of SPD available, including surge arresters and transient voltage surge suppressors, or TVSSs. Surge arresters are typically used at service entrances, while TVSSs are typically used at branch circuits. It is important to choose the right type of SPD for your application. Lighting is an essential part of any electrical system. The NEC specifies the requirements for lighting in Article 410. This includes requirements for the type of lighting fixtures, the location of lighting fixtures, and the control of lighting fixtures. There are many different types of lighting fixtures available, including incandescent, fluorescent, and LED fixtures. LED lighting is becoming increasingly popular due to its energy efficiency and long lifespan. The NEC also specifies the requirements for emergency lighting. Emergency lighting is required in certain buildings, such as hospitals and schools, to provide illumination in the event of a power outage. Motors are used in a wide variety of applications, from powering appliances to driving industrial machinery. The NEC specifies the requirements for motors in Article 430. This includes requirements for motor protection, motor control, and motor wiring. Motors must be protected from overloads and short circuits. Overload protection is typically provided by an overload relay, while short circuit protection is typically provided by a circuit breaker or fuse. The NEC also specifies the requirements for motor control circuits. Motor control circuits are used to start, stop, and control motors. The wiring for motors must be sized properly to handle the motor's current draw. The NEC provides tables that list the ampacity of different types of conductors. Heating, ventilation, and air conditioning, or HVAC, systems are an important part of many buildings. The NEC specifies the requirements for HVAC systems in Article 440. This includes requirements for the disconnect means, the overcurrent protection, and the wiring. HVAC systems must have a disconnect means that is readily accessible and capable of disconnecting all ungrounded conductors. The overcurrent protection must be sized properly to protect the HVAC equipment from overloads and short circuits. The wiring for HVAC systems must be sized properly to handle the equipment's current draw. Renewable energy systems, such as solar photovoltaic or PV systems and wind turbine systems, are becoming increasingly popular. The NEC specifies the requirements for renewable energy systems in Article 690 and Article 694. This includes requirements for the disconnect means, the overcurrent protection, and the wiring. Renewable energy systems must have a disconnect means that is readily accessible and capable of disconnecting all ungrounded conductors. The overcurrent protection must be sized properly to protect the renewable energy equipment from overloads and short circuits. The wiring for renewable energy systems must be sized properly to handle the equipment's current draw. Special occupancies such as hospitals, theaters, and hazardous locations have additional electrical requirements. The NEC specifies the requirements for special occupancies in Chapter 5. These requirements are designed to protect people and property from the hazard associated with these occupancies. For example, hospitals have requirements for emergency power systems and patient care areas. Theaters have requirements for stage lighting and sound systems. Hazardous locations have requirements for explosion-proof equipment and intrinsically safe circuits. As technology continues to advance, the NEC is constantly being updated to address new challenges and opportunities. It is important for electrical professionals to stay up to date with the latest NEC revisions in order to ensure that their work is safe and compliant. The NEC is a complex and comprehensive document, but it is essential for ensuring the safety of electrical systems. By understanding the NEC and following its requirements, electrical professionals can help to prevent electrical accidents and injuries.